Right, I think we can just start. Right, hi everybody, my name is Vikram, and today we'll be talking about how to evaluate the evaluators. It seems mysterious. If not, that's okay. There we go. What is this? Anybody? Bananas. Nice. What is this?
Unripe banana.
Unripe banana. Interesting. Still banana though. Plantain. Okay. What is this? Not good. Not good. Okay. I like that. When I think of all of those, to me, all of these are still bananas. All of these are just bananas. If you can get anything out of the talk, this is it. That's it. 5 minutes. We are done. All right. Let's get started, actually. So when we talk about evaluating anything, we start with traditional programming. How many people here are programmers as a background? Nice. Okay. How many people are product managers or don't have anything to do with programming? Marketing, anything else? All right, so I don't have to go deep into this. Okay, so traditional programming is fairly simple. You come in, you define your variables. So in this example, I'm trying to identify what is a cat. To identify a cat, I had to describe that it's a type of animal. It has 4 legs, 2 ears, and has fur, and it likes yarn and catnip. Traditional programming is fairly easy to evaluate because generally you are the one who's writing the code, or your colleague who's hopefully at the similar level as you are. And the logic is deterministic because you can walk through the whole tree of call and see exactly what is happening at each step. The outputs are predictable because you know that the output is only going to be a number. Or if you have a range in there, you know exactly which range your output is going to be in. But what ends up happening is most of the traditional programming is very hard when it ends up coming to traditional or to handle more complex patterns. So for example, here we are trying to identify what is a cat versus not a cat. Our example of these 4 or 5 parameters might end up falling short because you might end up categorizing lion as a cat as well, which it actually is true, but still. You want to be more precise in your calculation. So that's where we have this wave of neural networks that came in 2012, where we started doing a lot of machine learning models which were able to figure out differences between 2 different images of a cat versus not a cat. So traditional ML also has a very robust set of metrics that you can use to determine if that's if your model is performing well or not. So this is driven by the learned patterns. I just want to make sure. All right. Yeah, okay, so this is driven by learned patterns. So you train your model. How many people have tried training any model? Doesn't matter. New generation, older generation. Nice, okay. So when you train your model, you just have a lot of data set that you use. Your model is just a pair of programs where it's a big network. You pass in your data, it learns from the incorrect mistakes, incorrect labels that it does to figure out what are the correct responses in here. So based upon that, traditional models learn patterns. And then they can handle complex patterns as well. And you can, like this example, if people remember the Silicon Valley TV show, the seafood app. I actually found this on Google Play Store, which was very interesting. So you can use very well-defined metrics to evaluate and improve your models. It's very important because when you generate or when you fine-tune a model, or when you do your first model, you need to figure out how good is it. So to do this, there's 2 different kinds of models generally we talk about, classification versus regression. So classification is looking at this group of dots in here for green versus blue and trying to figure out where should I draw the line to say these are all green dots and these are all blue dots. That's a classification problem. Regression problem is generally saying if I give you an input, what is going to be the output? And you're trying to figure out that output line. So in this case, an example would be figuring out the cost of a house. If I give you a few inputs, what would be the cost of a house in there? So that's the classification versus regression model in here. For classification metrics, we have fairly well-defined metrics in here. Classification has been a problem around for a while, and that's why all the metrics around this are very well-defined. One of the easiest one is accuracy. Everybody goes for accuracy in here, where they want to figure out the number of predictions that we did. Out of that, how many were totally correct? So 100% correct predictions out of all the predictions that we have done. Then there's precision. Precision is saying that, hey, yeah, I could have predicted a model to say this is a cat versus not a cat, but there are often times when I might do things wrong. Those are false positives, things that are incorrectly labeled as the correct thing. So what you want to do is, in precision, you are trying to figure out true positives out of all the positive predictions, so that you know exactly how well my model is doing. So there's accuracy and then there's precision. Then these two metrics by themselves were not good. You also start looking at a recall. So if I have shown you a picture of a cat in training time, and if I show you the same picture of cat during inference time, can you actually figure out if it's the same cat? And how many times are you going to make the mistake of not categorizing it as the same thing? So remember, just going back, traditional programming, you always give, if you give input X, Y, Z, you're always going to get the output A. Does not matter how many times you do it. But in neural networks, it's very different. You could give the same image 50 different times, and you might end up seeing a different result, because the logic is not straightforward. Logic is not well defined. It's the model itself, which tends to, it might be always close in there, but if you look at the accuracy, or if you look at the precision, or any of these other metrics, they might be slightly up, slightly down from a mean value that you're looking at. So we came up with this metric called F1 score. F1 score is a mean of precision and recall. So you're trying to figure out how accurate my model is in the precision part, and how well can it recall things that it has seen. So if you have, in the past, if you have trained your model on a specific data set, so this is very useful in healthcare sector, where you want the model to be predicting the exact thing that it has been trained upon. For fever, if you are supposed to take medicine A, the model can't be suggesting medicine B at all. All of these still started to fall short. So then we had new metrics come in, which is ROC, which is, actually AUC is the better one. Forget about IOC. AUC is area under curve, and you're looking for the metric around F1 score, precision and accuracy. You plot them on a graph, and then you see what is the area that's using in a graph, and the better that area, the better your model is doing. So that's what generally people are using on all of the classification-based models. Okay, then we go to regression models. So here we have three, MAE, MSE, RMSE. So these are all fairly simple way to say mean, average, squared difference, then the second one is squared, and the third one is root mean squared. These are just way of saying the mathematics works. The way mathematics works is, if you end up doing the absolute differences, the model tends to go very high back and forth on correct versus incorrect. So then you try to do a square difference. It actually becomes better on prediction versus actual. And then the best way to determine that is the square root of the mean in there. And if you do a square root of mean in there, it becomes much better on, the model doesn't deviate much from the path that it's trying to do on the regression side. So how would you do this? If the price of the house was supposed to be $1 million, but the model predicted actually something less than that, you take the difference between the error. So let's say 900K versus $1 million, you take that difference, and that becomes error for 1. Then you do this across 50 different other inputs. You have 50 inputs. Now do you do the mean, and that's the MAE. Now you square it, and then do the mean, that's MSE, and then you square root it, and then RMSE. These are just ways to get the better metrics, better understanding of regression in there. Okay. Then came these Gen AI models. How many people have played around with these? Nice, okay. So how do these models work? They are trained upon a lot of data, and what they can do is they can start generating new data. Oftentimes, they might take the data that it was trained upon and put it out verbatim, but it's less often than that happens, mostly because of, I think, the way people are asking questions in there. So, okay, for that, we will start with here, actually. So this is Google AI Studio, and I asked, the model in here is Gemini 1.5 Flash, and I asked it a function to write a function to calculate the distance from Earth to Moon. So this is very simple prompt that I gave it. Did not give any system instructions. You can see it's empty, and this is the whole function, whole ask that I had in here. This is the output. For anybody who has done any physics, there's actually no easy way to figure out the distance between Earth and Moon, because there's a lot of gravitational stuff that keeps going on. But the model does a very good approximation in here. It uses a lot of constants. Oh, the function does a very good approximation here. It writes the constants in here. It uses the date to figure out where in the moon cycle we are. And based upon that, it figures out the orbital distance. Oh, I'm not trying to edit it. It's fine. Okay, and it writes the whole function. Then it gives the explanation as well. So it tells me exactly why or what we are doing. So it tells me that we imported math function from Python. We defined specific options in here for the distance. We calculated the days since pedigree. Then we calculate the distance based on all these parameters. So how many people think that this is a good answer? If you think it's a good answer, please raise your hand. It's not a trick question, it's a fairly good answer. Like, I'm not trying to trick anybody. But the question now is, how do you evaluate this? When I look at this answer, how do I say that this is a very good answer? Because yeah, these constants that it's using, they are coming from probably NASA's website, so they are fairly accurate. But what about, rather than 322, it might be, rather than days, what if I wanted this to be in hours, because I want more specificity? So then I'm, as an engineer who's working at, like for me, I don't care about the specificity in here. But somebody at NASA who asked the same question, they might have, no, this is wrong, because this needs to be in hours, then only I can calculate the orbital velocity, and then I'm launching a rocket, I need to be more precise than this. So for them, this answer might be very wrong. So figuring out the responses that these models are generating, it's going to be very person-to-person based. And that's one of the biggest challenges that we have right now in Gen AI-based models. To figure out any output that is being generated by these models, how do you evaluate those? And after evaluation, how do you even take those evaluation values, put them back, and make the models even better? Because generally, the reason you do evaluation, the reason we did all the accuracy and other stuff in here, was to figure out, okay, if my accuracy is bad, I need to put this kind of data set. Let's say I was training a model to figure out different animals, and my accuracy was really bad on cats, which means probably I need more different kind of examples of cats. Let's say my accuracy was really bad on cats in dark lighting. So I will add more data sets of cats in dark lighting so that my model gets better. So what you are doing evaluation, you're using generally these, your evaluation feeds back into the model development lifecycle so that model gets better. But sadly, we don't really have good ways to do this on generative AI interface. So today I'm going to talk about how exactly, or whatever we have right now, and where's the future going on, and possibly a solution that I have. We'll see how people like it. Okay, so the first one is blue. This is the score that you do to the model to give it how well does model memorize. So it's bilingual evaluation understudy. This score was generated for translation tasks. So most of the things that you will see in evaluation in here, since the field is so new, we don't have good ways to measure things. So what we are doing is we are trying to identify things from the past, older models, older ways of doing things, and trying to retrofit them for Gen AI. It's not my phone. I don't have Android anymore. I remember that as an Android call. Okay, so blue is bilingual evaluation understudy. What it does, it compares the n-gram. Are people familiar with n-gram? No? Okay. N-gram is essentially saying that, hey, I take 3 words in here, compare, n-gram, and overlap, and then I start using that as an overlap between other words to see how many words match this exact overlap. So n is the number of words you want to include, and you're trying to do overlap on n grams. So it's like generally trigram score is what people know about when they're looking at memorization score. So trigram scoring is you take a set of 3 words and you try to figure out how well did the model do between the original thing that it was supposed to generate and the thing that it generated, and then you try to compare those as the 3-word score. The issue here is that it's very sensitive to word order. So if I move this n-gram to over here after the overlap, it will perform very differently. The score will suddenly drop. So when the models, when you can write the same thing, like let's go back to our example in here of this Python program. In this example, if Earth radius was moved down here, our blue score will be totally off the beat, like it will be totally drop quite a lot. So that makes it so bad, because when you're generating the model, the way I write Python program versus you write Python program would be very different. Maybe I do my variable declaration always alphabetically, versus you do it based upon the number like that is in there in the back. So based upon that, it ends up failing quite a lot where the word order comes in. And with Gen AI models, that's actually very often that it comes in. It also ignores the semantic meaning of the words. So in this case, I'm saying overlap between generated and reference. You could rename this and say commonality. Rather than saying overlap, you can say common words. As soon as you do that, 0. The blue score goes down. Even though the answer is right, but the blue score goes down. It also requires reference text. Think of this. A lot of people are using these Gen AI models to write fantasy fiction. How are you going to get reference text for fantasy fiction? There's no way to get that. And how do you evaluate then if you don't have the reference text? So what ends up happening is when these models are being built and being evaluated, you don't have a good reference text, and that's where these models are. This metric itself is not useful at all. So when you see that companies claim that they have very good scores on programming now, when their models have very good score on programming, they're comparing it against some of the specific data sets that they haven't built. And that's why there's often the case where there's no metric out there right now to calculate the fantasy score. If I ask a picture of an avocado couch, there's no metric out there to measure that. And Gen AI models are being used for that. So how do we start calculating those? We don't have a way to do that. Okay, so this is just an example. I found this GIF at the last moment, so I ended up adding it in here. What it's doing is using the git diff to figure out how do you do the blue score. So this is just the same thing that I was talking about, n-gram. So it's taking the difference between both of the original input versus the generated output and trying to figure out where does the blue score come in. So this is at 90% in this example. Okay. Then next, we have Rogue. Rogue is summarization score. So you take a text and you figure out how well was this text summarized in the output. So let's say you started with a book of a lot of text values, and then you try to figure out how well the output that is generated out of this summarizes the main concepts. So this was generally used for summarization use cases where you would go to a news website, and then a news aggregator like Google News would take the content from the news website and show you the headline or show you like the first few snippets. Google search, every time you go to Google search, it shows you the title of the website, but also some snippet around that. This score comes from there. So it says, how well am I taking the content of the page and putting it back in here so that folks can understand exactly what is happening in there, in the original content. So it's very similar to Blue, the way it works, but it's more focused on summarization. But that causes it to miss on the creativity aspects. So anytime there's more creative stuff happening in the model, it can't figure out anything in there. And it also requires generated and the reference. So it still requires the original data set in there for you to compare against. Then we have Meteor. So this is mouthful in here, metric for evaluation of translation with explicit ordering. So you try to make sure that the order remains correct. So this is more useful for programming tasks because you can't have a curly brace, like a closing curly brace before an ending starting curly brace. So in those examples, the Meteor-like values come in very well. So it's a combination of Blue plus synonyms plus paraphrasing. So what ends up happening is, you remember Blue, where you're just trying to figure out how many words are matching. So you take that normal word order. Then you are able to replace the synonyms in here. So in this example I was talking about, rather than using overlap, I end up using another different word. But if that is the common known synonym, then the score won't drop. So you made that better by adding synonyms in here. Then you also add paraphrasing, which comes from this Rogue summarization. So Rogue was giving you the ability to take summarized words and give a good score on that. Meteor takes that in here as well to say you can take the same text and paraphrase it in a different way, and that comes from a different model. So in this example, the WordNet is the dataset that we're using to get the score, but it ends up becoming really really good metric in here. But it still fails. It still falls short. Where does it fall short? It relies on external sources. So in this example, we have synonyms. Somebody has to write those synonyms. Generally, you can find those on websites, on examples. There's datasets out there. Similarly, for paraphrasing, we have datasets out there, but they might fall short. They might not be up to the date on, let's say, if you're doing it for scientific evaluation. Most of the datasets out there are not good enough for scientific evaluation because they don't have good synonyms, good paraphrasing of the same thing. When a doctor writes a note, the note that they are written, it's generally fairly straightforward and complex. And if you're using a metric like Meteor in there, it doesn't define well into the score might vary a lot, while the response is actually very good. So it does not capture all the details in here. And in the end, since we are using Blue in here, it still struggles with semantics in here. So if you end up changing the meaning of the word and everything else remains same, your meteor score might still be high, but the words might not make any meaning. So grammatically, it might be correct, but there's no meaning at the end of the, you read the whole sentence and you're like, what did I just read? Like you read the thing, it makes sense word by word, but overall sentence doesn't make any sense. So for example, cat, 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 cat might give you a high score, but doesn't mean anything. Okay, so then we have perplexity. So the best way to think about this is, I promise this is the last slide on this metrics. The lower the perplexity, the better language understanding. So this is more about understanding of the language. This correlates with fluency. So again, the cat, cat, cat example. If your model can predict the next word very well, cat sits, cat sits, cat sits, it has a high score. Doesn't make any meaning, there's no meaning at the end of it, but it gives a very high score. So all it's doing is it's trying to figure out what is the next word that should be predicted, and is the model predicting the next word correctly? So the biggest city in US is, I actually don't know the answer to this, but whatever that word is supposed to be, if that is the answer every time, then the model is right. But if the answer is not correct in there, then the model is wrong. So it generally works out very well for factual-based questions, but it does not measure any creativity. So anytime there's a creativity involved, you can't measure that in here. And it's very sensitive to training data. So if your training data was 5 years old and it talked about, I don't know, COVID at that time, how COVID was raging over the world. But today, if you ask the same thing, the model, like normal news sources and normal Google search might give you a different response versus what the model might do, because it's very sensitive to the data that was trained upon, versus today, it's like the world is totally different. Okay, so the best way I like to think about this is it's a fluent parrot repeating gibberish words, and that would score high on perplexity as well. So why is this so hard? What are we still missing in here? So some things that I like to think about is we are missing coherence in here. Coherence is when I'm talking or when I'm writing things and you read that, can you understand that? Can you see the logical flow in there? Oftentimes, when I first make my first version of the slides, I just put things in there, random slides at random locations. They don't have a logical flow in there. So when you look at that, it's like, yeah, I see there's a lot of content in here, but there's no coherence in here. I can't understand this. How does the first slide relate to the second slide? Why are these in here? So that coherence as a metric is not present right now. Even perplexity, which talks about the next token, comes very close, but it's only for factual information. It has nothing to do with when we talk about creativity. Relevance is missing. So measuring how well my text generates or aligns with the given prompt. So this is the part that is out there right now. When you ask a model to do something and you mention a very specific word in there, and the model doesn't end up using that word. So for an example in here would be, you ask for write a story about an elf from Lord of the Rings to do XYZ, and it ends up writing a story about Harry Potter's elf. Very different types of elves. So the difference in here, that relevance score is missing. So it missed the part about Lord of the Rings versus Harry Potter and ended up writing very different stories about the elves that were out there. Then factuality is missing. When you look at these responses, for very specific questions, you can measure the accuracy. The perplexity metrics does that. But again, it depends upon when the model was trained on. So based upon today's information, if the value is inaccurate, then there's no way to measure that factuality right now. And finally, the informativeness. So you ask a model to do something, it generates some output, but how much useful information is it conveying to you? These are some of the things, some of the metrics that are totally missing right now from model evaluation right now. So when we talk about, okay, then how come all of these companies, every few days, there will be a new model, and they will claim that, hey, my model is better than your model, or model X is better than other model. How are they doing this? The biggest thing that I would say in there is like, we'll come to that, but when you look at those benchmarks, the first thing that you should think about is, how well does this translate to my use case? Sorry, how well does this translate to my use case? If it doesn't translate well to your use case, doesn't matter what the score is. If the score is really high on math and you're not doing anything with the math specific in here, does not matter at all. Okay, let's take a look of how exactly are people doing this. Let me see if I have a slide for that. Okay, yeah. So how are people doing this right now? The best example that we have out there is called LLM Arena, and this is LLM Arena. What ends up happening is you come here, you give a prompt in here. So I wrote the prompt, which is the same thing that we asked, write a function to calculate the distance between Earth and Moon. It takes the prompt and has two different models. We don't know what two different models are. And it uses those to generate the response. So this is his model A on the left side. It generates the response. We see it's similar to the model, the response that we generated earlier. It broke the functions down into the calculate distance and calculate distance at a specific time. So it wrote two different functions. Like this one is actually fairly easy because the distance is equal to Moon's orbit. And it just calculated the distance in here. Did not write any function in here actually. But the other one at a time, it ended up using a lot of variables in here without giving me a lot of details. You see this, anytime you see math like this, like why is this a random constant in here? Why is this not a variable that somebody put it outside? So I know what it is. It's just a random value in here. So what you end up doing is you look at this response, then you look at the other response in here. So this model, this function was like, okay, Earth to Moon distance this is the average, that's it. You don't need to write any program. This is the output that I'm gonna just give you. Otherwise, if you want, I'm gonna give you a unit so you can, rather than asking kilometers, you can ask for meters or miles in here. So what you do is you end up coming in here and you look at, okay, which model did better? Any thoughts? Model A or model B? B? Really? Because B just gave you the random value.
Yeah, but we was thinking about, well, you could be from the EU, so you got kilometers. And then
Perfect. This is the great example here. Now, at this point, if I took a score between everybody in this room to figure out A is better or B is better, how many people say A is better? How many people say B is better? All right. I'm sure everybody has reasoning on why A is better versus B is better. I don't know. I can't tell. I don't have an opinion, but what you end up doing is you end up coming in here and you say A is better or B is better. And what they end up doing is they use or both are bad. You can do that as well. And then based upon that, they generate this leaderboard. So this leaderboard essentially says the models are hidden in the background. You don't see which model generated what. But you end up coming to this leaderboard and see, okay, based upon all the scores, all the people, this 24,000 votes versus 19,000 votes, what we can tell you that GPT is performing at this level, Gemini is performing at this level, and at different dates, different models are performing at these different levels based upon what people on this website have come in and voted on. This is the best metric that anybody out there has right now. Anytime GPT will break this score, they will come in and claim on Twitter. Anytime Gemini breaks the score, they come and claim on Twitter. This is the best metric out there, just so people know. That's where we are in the world. Okay. What are the challenges? Even with that modeling, what are the challenges that we have? We still don't have ground truth. We don't know what is the right answer. The same function that I wrote, again, as the person here said, like, they like the second answer. I don't know if that is the correct answer, or even if the first one is the correct answer. So correct answer is like that correctness is still missing. Second part, the UX of the model might determine whether the accuracy is good or bad. So for example, a model that performs really well on math tasks might actually perform really bad at any time you're trying to use it for fantasy fiction writing, because it has zero creativity. All it knows is 1 + 1 is 2. This is the same reason we talk about, like, in humans, the right brain versus the left brain. Those are like actually generally, like, just so people know this, that's false. Don't think about that. But the way people think about it is like left brain more creative, right brain more analytical, and people end up being like that. But that's the thing that ends up happening with the models as well. If a model is really good at math scores, the model might not be as good on creativity side. Then there's adversarial things in here. So we saw this example of distance between Earth and Moon. You know, I can change the response of this just by adding 1 or 2 words. If I add 1 or 2 words in here, the model might respond totally differently. Has nothing to do with the rest of the question in here. I might add just A, 4 in there. It might change the whole response. That adversarial part in here causes it to be so weird because, like, what? I just read the question, and there's just like 4 characters at the end. Why are you worried about that? Just read the rest of the question. But models take those inputs and just behave totally differently. Okay, so what is the best solution that is out there that people are thinking about, that everybody else has built in? And especially when we come away from these benchmarks and leaderboards and everything else, where you are thinking about, when you're thinking about your own use cases, sorry, I end up doing this often, when you're thinking about your own solutions. So we come to homegrown solutions. In homegrown solutions, this is what it looks like. I'm just going to show the sheet so people can see. You have a system prompt. So this is a system prompt that you wrote. You have a user prompt in there that you would write, the question that user is asking. So let's say you built a website for saying, hey, this website will give you the best mathematical answers. And then people come in, they ask for questions. In the system prompt, you might have, hey, you are the best LLM agent for mathematics. Your response should always be in mathematical provable way. So you write a system prompt in there. Then user comes in, they ask the question. At that point, you might also want to retrieve some documents. So if people are familiar with RAG, which is retrieval augmented generation, which means, let's say if you're trying to do a physics question on specifically trajectory of like the distance between Earth and Moon, you might want to go in and fetch the document from NASA's website because they have the best information out there. You fetch that document, you add that along with the question that user has asked, so that when the response comes out, it includes the information from those documents, because those documents have the better constants today, or any other information that we are missing right now, like weight of the moon. I have no idea. I don't know if that matters in the distance, but you might be able to get all those documents in here. And then you try to also figure out what is the latency in here. How much time did it took you to go to NASA's website, fetch the details, and put it in here? Then you look at the generated response. What is the output that was generated? The latency for that response generation, and then whether it used any of the documents that you sent in here. So oftentimes people might be asking 2 + 2 is what is the value, but you might end up going to a like elementary mathematics notebook. You're going to fetch that whole notebook in the RAG documents and then generate the response. Was it even used? If it's not used, why are you doing this? And then finally, what is the golden response? What is the actual output that should be there? And then these are the things that humans have to do. They come in and look at what is the tone of the answer. If it's a mathematics website, the tone should be very professional. The model can't be joking. The model can't be putting emojis in the responses in there. Then style. If you're doing Python programming, are the tabs properly set? If the tabs are not set, the program might not compile. People will say that, hey, the model doesn't work. So you have to focus on the style as well. And finally, the accuracy, like if you got the right value or not. And again, these are just sample things in here. People have a lot of different things in here. People have a sentiment score. People have frustration. You can add whatever else you want. But the thing is, there's humans who are going to be evaluating these values. OK, so let's go back to the slides. All right. OK, so yeah, we talked about some inputs. So in this case, inputs are system prompt, user prompt, RAG documents, and the latency for that. Then the outputs, which is generated response, latency, and documents used. And then evaluation, which is based upon the golden response. So you look at the final response, what it should be, and then you compare it against the generated response, and you try to figure out, is it accurate on the tone, style, and accuracy part. OK, the best solution that is out there right now that I've been looking at is called LLM Comparator. So this is by Fair team at Google. And the thought that they went with in here, this is very interesting, is what if, when you're trying to compare models, rather than have humans come in and give the answer, what if we use the tactics from UX research? Anybody here who has done any work on UX, user experience? OK, nice. So when we go into user experience, we ask questions, but in a very different way. Like you might ask the question 1, which is, would you like the values to be in like dots on like bullet points, versus would you want 1, 2, 3? So you can ask the questions in a prescriptive way, versus you can also ask the questions in a very different way where you show that in the examples. Do you want bullets? One example is bullet, one example is 1, 2, 3. And then you switch the examples 3 slides down, 3 questions down, and have them pick the same answer. So this technique, I don't know what it's called. I'm really bad with names. I think the series or the trick here is you ask the question in X, and then you ask the question is negative X. And if the answer for both of those is actually matches, then you're good. Okay, so you ask the same question in 2 different ways, X and negative X, and if the answer matches, then you're good. But now, how do I ask these questions to humans? Because humans are not easily scalable. Plus, in companies like any tech company out here, tech worker wages are really high. You don't want them to sit down and do evaluation. So, and you can give this task to be outsourced, but then you worry about the quality. How are they evaluating? Do they have access to all the documents that you're using? So what you end up doing is this thing called using another model. So this is LLM Comparator. I just installed the dependencies, and In here, we have 3 different models in here. So one is LLM judge. So you take another model that you define as you are the judge. I'm going to ask you questions in 2-3 different ways, and you're going to judge the responses that are being given to you to calculate how good are the responses out there that are being generated. Then the judge also has to give rationale on why does it think that the responses are correct, and then it has to cluster those responses to figure out, this is more for, this clustering is more for us to figure out like which category of responses are well, which category of responses are bad. Okay, so in this example, I just ran it on GCP. This is Vertex AI, and I gave it some examples in here. So this is a prompt, and response A is good. How are you is the question, and there's response from model A, response from model B. And what you can do is you can have this generated based upon 2 models that you're trying to test today. And you just generate this JSON in here. Once you have that, you pass it along to the model, and this is just a lot of helper functions in here. It generates, runs the evaluation. This is running the evaluation, 18 examples. What ends up coming out is this response. So this is a fairly simple one, so we'll walk through here, and then we'll go to the bigger one. First of all, as soon as you start here, you can look at this score distribution. It tells you exactly how good the model is doing, model A is doing versus model B. Very quickly, you can see model A is doing better. This is only 2 examples in here, but you can see that model A is doing better than B. How well is it doing? How often is it winning? So you can see win rate in here. And then why is it winning? So there's the answers in here. It's like A is better because it directly answers the question. It gives a suitable response. It's a direct response. All of these are, again, since the data set is only 3 questions and they are based upon like hi, hello, you don't see better clusters in here. But let's go to a proper example in here. So this is LM Comparator website where they have a lot of examples with different kinds of tasks in here. So there's creative writing, science and technology, coding, math in here. And what you're trying to do is there's 2 different models that the team, this is example data set on which they did. This is Gemma 1.1 and this is Gemma 1.0. So they were trying to figure out how good the 1.1 model is doing on 1.0. Actually, when you look at the responses in here, I don't know if A is better or B is better. It seems like Gemma 1.0 was actually better than 1.1. So overall score distribution, you can see how the model, the evaluator model, is rating the overall responses. And you can see different categories as well. There's science and technology, coding, math. So you can see, okay, humanities, it's doing much better. Model A is doing much better. But on business side, model B is still doing better. Or actually, it's wrong. Like I'm looking at the numbers in here. So model A is still doing better. This is the only part where model A and B don't have good responses between like A is doing better or B. Then there's summary. Is more concise, directly answers the question, is more creative. And then this is the first part that I love, is oftentimes you want the model responses to be short. So you look at the word count in there. One second, I just want to do a time check. Nice, okay. So you want to do a time, you want to do a custom functions in here to check like, hey, what is the word count? So if you want smaller answers, you're looking for, okay, B in this case and A, generally like both of them are similar in the word count that is being generated. Does it contain bulleted list? If you are trying to train a model only to be responding in bulleted list, then you can use this as a response. You can create new functions in here. So if people have seen, there's a paper out there or some study that somebody did, which is most of these models are starting to add some new kind of words in there. So something like, I forgot the word, but it starts, this is a good example, it starts with sure. So most of the generated, when you ask somebody a question, they don't say sure, then answer the question. So if you're trying to determine if the response was generated by a model or not, this is a fairly simple function. If you see that the model responded with sure at the beginning, then it's probably being generated by NLM. And we see that model A, which is our 1.1 Gemini, is doing much better because it's generating 0 such responses where it starts with sure. So you know that it's actually doing better in this case. And you can keep adding your own functions. These are Python or JavaScript-based functions that you can keep adding in here. Then you can also end up using cloud APIs. So this is in here is using cloud APIs to see toxicity. So this is the score in here, 0 to, I think, 1 in this example. I don't see the numbers in here. But how toxic the response is, how sexually explicit content is, how violent it is, and you can keep adding more in here. So you can create more different endpoints that you can call to evaluate your model, and you end up seeing everything in here. And you can come in, see exactly what the responses were, all the details out here. Okay, the next one that I want to show you is this language interpretability tool. This is a little bit digs deeper to see when the responses are generated at the end. Like here you got a good cluster response. Oh, sorry, let's go here. So you got a good cluster response in here to say contains headlines or contains headings or not. And now based upon that, you want to figure out how well or what was the kind of responses that are coming in where it's doing very well, which is on the left-hand side. Like this is a 3D score in here. So this is the embedding of all the responses. So you look at how well are the things that are on the very left versus these here. These are the ones that are causing the model to fail or fail often, where it's like sometimes generating, sometimes not generating. This you want a boundary to be very well separated boundary. This boundary is not right now, not well separated. If I zoom in, I can't. This is like, you need mouse to do this. I can't do it with this. And you can also look at these. So there's like different views in here. You can look at specific example by example. And this is also by Google Fair team, which does all of these. Both of these projects are from them. So finally, here's the solution. We are probably 3 to 4 years away from a decent solution. Nothing is out there right now. This whole talk was just to give you an input to say, hey, you should probably start looking into this. And if you have a good solution, you can probably go to market today and get a lot of money. But until then, it's all bananas. So that's it. Thank you, everybody. Slides are there. That's the QR code for slides if anybody wants those. And yeah, I'll be around for questions. Thanks. Good?
I have a question.
Oh yeah, go ahead.
So when you said about like the creativity of like the models, so does the creativity means the temperature setting of a particular like model or like how we're training that thing?
So let me just show it to people. Okay, so here we go. There are few things that you get to play around with the model when these model products are giving you. This is one of those things is called temperature. Temperature just says that when you generate the next word, which word should you pick and how random can you be in there? So the smaller the temperature, the more random it can be, which generally correlates to creativity. So in here, when we generate this response again now, so we rerun this, it's being more creative now. Actually, I asked the question which is not creative at all. But let's say, what is the moon in one of the fictional stories? Tell me one of the examples, I forgot. Alpha Centauri. Yeah, I know. Let's figure out something. Okay. Still not creative. Let's just say, write a fictional story about elves from Middle East. Oh no, Middle Earth. My bad. In today's world. Okay, so this right now is fairly creative right here. But if you increase the temperature to be higher and higher, the creativity drops generally. So this is just a control that the model providers have given you. These have nothing to do with evaluation of the model. So evaluation is a very different story at the end of this to figure out how well the model is generating those responses. When we generally do evaluation, we keep the temperature to be 1, and then we just do evaluation. Or you set these values. Doesn't matter what it is, but you set these values, and then you do evaluation. More questions? Or hopefully I answered your question. If not, please find me outside. Yes?
Isn't there a worry that having an LLM read another output and rating it and feeding that back into LLM, you're going to get almost like LLM inbreeding?
Yeah, breeding. All right. So yes, it's totally true. But what we are trying to do is, okay, so this is a characteristic of if you read any of the scientific literature around how do you make your teams go fast. So one of the best examples or the best advice out there is make sure they can experiment fast. Now, how can a team experiment fast? If you have test cases, so let's say this is a normal software development environment. If you have test cases, your teams can write new code much faster because they have the test cases to make sure that when they write something incorrectly, it fails, and then things don't get deployed and doesn't cause a havoc in here. This just allows you to do a quick first run evaluation. This gives you a lot of information about how well is your model A doing on model B. And you can have your own metrics in here, like the way we were talking about, starts with sure or not. And if you're trying to go focus on that, you can say that, hey, now my model is doing very much better on this based upon this evaluation. Now I can take this when I'm doing the final evaluation, and at that time I can have the humans come in and do a secondary evaluation. But when you're trying to go fast, you can't be doing this every day. And I'm sure there's teams who are training these models every few days, and you run 50 different evaluations. You changed the document store. Let's say tomorrow you added 50 different document files in here. Now you can't have like your team come in and do the whole evaluation again. So what you do is, with these, something like this, it gives you directional input. Are you directionally moving correctly? If you're moving in the right direction, then it's fine. You can, once you are done with your multiple experiments and before release goes out, you can come in and test. So I totally agree. It is a thing everybody's top of mind, but since there's nothing better than human evaluation, this just gives you a proxy right now. Go ahead.
I was wondering what the thoughts were on having something set up like a checkpoint, sort of like in video games where you have a definitive point where you can always go to. You mess up, you go back to the checkpoint, saving on everything on back end. Wouldn't that be something to incorporate here?
So those are things that are already out there, and that's why you see the teams will release GPT 1 versus 4.5, or 4 versus 4.5. The reason is because in between those, they are probably doing hundreds of evaluation. So those are the checkpoints that they use to say, okay, let's say 4.1 is doing worse than 4.1.1. So then you can go back to that model and use that as the base to start training more. So you figure out, you do multiple checkpoints at multiple levels, but now you can't have your human evaluation team come in and do this evaluation every time. So you can use these checkpoints to diverge back and forth. Good? Yeah.
I have one more question.
Yeah.
So like,
There's, by the way, lunch is out there. I'm just here answering questions, so please go for it. Yeah.
So, when I was looking at this one, so all right, so like how does the red teaming, like when you do like a red teaming like test on like large language model, how does it affect the scores like with respect to the change in like the data that it's been given? Because most likely, if you're going to do red teaming across a lot of different models, they would be getting data from like, I'm saying like internet, so like a public source.
Yeah.
The data will be biased in different ways, so the tokens will be skewed in a different way.
Yeah.
No matter what you do in terms of generating your vocabulary, the tokens and everything, it's always going to be skewed.
Yeah.
But when you do red teaming, you have to make sure, as I said, the best evaluator is the human feedback in this case. So how does the human like encounters this thing and like fixes that issue?
Perfect question. This is not for that. For red teaming, what generally ends up people doing is they do all of that in the data part. Before you train the model, you do a lot of things to make sure that the data that you're using, is better and has been done multiple iterations on it to do red teaming and like all the cleanup of the data. All those are before the model evaluation. So if you look at, if people haven't seen this, Gemini paper has a really good example of red teaming in here. So they have a really interesting harm-inducing queries where they look for, okay, they have a team which is just all, if people don't know red teaming, that means essentially adversarial team. So your 90% of your team is working towards making something good, and there's the 10% of the team which is trying to break that. And this red team's job is essentially to find out these questions, these queries, or this data set that they can use to poison your model, or to ask the model a question that it might not give the right answer on. So generally, all of these things happen before the model is being trained upon, but at the end, they also have something like this, where harm-inducing queries come in, and they try to make sure that the model is actually filtering on those, so that it does not generate the response. But the best thing that's out there, just so you know, is there's something like this, which is, it's not here. Oh, right here. Edit safety settings. So what ends up happening is you generate the response, then you ask another model to evaluate the response on a few categories that you're worried about. And then you say, okay, what is the blocking criteria that I want to use? And based upon that, you block the response from being shown to the user. So model still generates the response, you evaluate it, and then you don't show the response to the user. It is the multi-agent part where like the first model generates the response. So let's say if I do this block most, and then I ask a question to say, Hopefully this is not recording anymore. How would an elf curse a hobbit? So you see this exclamation mark in here. The model very quickly stopped generating the response because it figured that it was probably doing something that was a harassment or something like that. So model quickly stopped generating the response. Or the secondary model stopped the first model's response from being shown. Go ahead.
I know some models have restrictions where you can't use it for training other models. Exists or this fall outside of that because it's evaluating?
Yes, generally. I totally understand what you're saying. I just don't have a right answer because it's more legal stuff in there. But generally, when you're trying to do this, you have this third-party model to do evaluation. And based upon that, I think the biggest worry that most of these companies have is you use their responses to train the model, which is very different than using those to do the evaluation, since you're not using the text as is. This is same as the copyright law. Like you can right now go to Facebook and talk about Harry Potter, but you can't take the Harry Potter textbook, or Harry Potter book, textbook, it's not a textbook, Harry Potter book and make a copy of that. So it's like similar to copyright law. Go ahead.
Which model, I know GPT-4, all the papers say GPT-4 is the best evaluator, but which other models we're considering?
So when people ask me, I just tell them to go to this page. Because human feedback, I can't give you a right answer, so take the response from other people. I think we'll stop here and then I'll be around.
Thank you so much.
Awesome. Thank you, everybody.